Good morning, students. Next chapter is thermodynamic and kinetic aspects of metal complexes. In this, we will discuss about the thermodynamic and kinetic stability of metal complexes. Firstly, thermodynamic stability of complexes. What is the thermodynamic stability of a complex? That means the compound exists under stable conditions or not and may be stored for a long time. कि whether a compound exists or not and that can be stored for a long period of time, that are stability of a compound. So the term stability or instability that can be explained in terms of two terms, that will be thermodynamic and kinetic. Firstly, we will discuss thermodynamic stability of a complex, that is the measure of the extent of formation of a complex at equilibrium. For example, copper 2 positive plus 4 ammonia, then there will be complex formation, that is tetraamine copper 2 ion. In this, if we take equilibrium constant Ks is equal to product concentration divided by reactant concentration. Product is complex ion divided by reactant copper 2 positive and ammonia the power 4. So Ks is directly proportional to complex formation. So we have to proceed the reaction in forward direction. It means more the formation of complex and more will be the stability of the complex. So Ks is directly proportional to complex ion concentration. So larger the value of Ks, then that will be more will be thermodynamic stability, and therefore Ks value that we should be greater, then there will be more complex formation and that will be more stability of that complex ion thermodynamically. And in this we take one is metal ion, other is ligand. So if metal and ligand interaction is strong, then there will be more stability and more bonding interaction will be more, and then thermodynamic stability will be more. So if we take another example, copper 2 plus 4 Cn negative ion, then there will be complex ion. Then Ks is equal to complex ion divided by reactant copper 2 positive and Cn negative. Then in this K value is Ks value is 2.0 into 10 raised to power 27, and in above case that is 4.5 into 10 raised to power 21. So 10 raised to power 27, that is more value because Cn negative is a stronger ligand than ammonia, therefore more interaction between metal and ligand copper 2 positive and Cn negative ion. So more will be the stability constant and more will be thermodynamically stable as compared to copper ammonia complex. So there are so many other examples. Next is, if we take reciprocal of stability constant, that is 1 by Ks, called dissociation constant, and that is represented by K dissociation, and it will be inversely proportional to stability constant. K dissociation will be equal to 1 by Ks. So K dissociation for the complex sign, that should be smaller for the more thermodynamic stability. So greater the value of Ks and lower the value of K dissociation, and more will be the thermodynamic stability of that complex. Next, there are two types of stability constants of complexes. One we will discuss stepwise stability constant, and other will be cumulative or overall stability constant. Firstly, we will discuss stepwise stability constant. In stepwise stability constant, firstly we will take metal ion plus ligand, then there will be complex formation, and K1 will be equal to product concentration divided by reactant M into L. Then in stepwise stability constant, Ml molecule that will add to another molecule of ligand, then Ml plus one ligand that will form Ml2, then K2 will be equal to Ml2 and Ml into L concentration. So if we have to make the MLN, that is the for N ligands, so that will be equal to ML n minus 1 plus 1 ligand, because in case of product mln and reactant is 1 less than the n value. So we take in reactant mln minus 1 plus 1 ligand, that will form mln, then Kn value will be equal to mln divided by reactant concentration. So there are K1, K2, K3 up to Kn, that are called stepwise stability constant. As we will take the value which will be more value K1, K2 or K3, K1 will be more value as compared to K2, because firstly one ligand is added to metal ion, then there will be complex formation. When another ligand molecule that is added to the complex, then already there is ligand, so that will be repulsion. So Coulombic repulsions due to, then there will be less probability of incoming of the second ligand. So K1 value will be greater than K2 than K3 value. Second is the cumulative stability constant or overall stability constant. In this we will take m plus l, that will form ml. In this, that is represented by beta 1 equal to ml divided by m into l. And in this we take double concentration of ligand molecule, we add into metal ion. So metal plus 2 ligand, then that will be equal to ml2, that is represented by beta 2. And similarly with m plus triple times ligand concentration, so similarly nl, that will form mln, that will be represented by beta n is equal to product divided by reactant concentration. So beta n is called nth overall stability constant or cumulative stability constant. Then we have to make relationship between beta n and kn values. So beta n will be equal to k1 into k2 into k3 up to kn values. So if you can calculate yourself between relationship between beta and k value. So beta 1 is equal to k1, beta 2 is equal to k1 into k2. Similarly beta n is equal to k1 into k2 into k3 up to kn. And if we take log, then log beta n is equal to log k1 plus log k2 plus log k3 up to log kn. Then log beta value, that should be more than 8, then complex ion is considered as stable complex. So these are the stability constant. One is stepwise and other is cumulative stability constant. Thank you, students.